I got there early. I have a special, very special guest speaker for you today. This is Mike Stengel. He's a senior in the Aerospace Engineering department. So 2 years ago, he was sitting where you were sitting, I think.
Yep. Yep.
He's also a pilot, and he's going to come talk to us about the pilot's perspective for Aeros. And as I mentioned briefly earlier, at the end of the class, he'll take questions, and feel free to ask him reasonable questions about the undergraduate experience at Michigan. All right? All right.
Thank you.
Do you need the lights adjusted?
Yeah, I was going to, just the front light is off. So.
Yeah, I think it's just that. Oh, nice spider. Does that help?
Can everyone see all right? Yeah. Good. You can hear me too? All right. So good afternoon. My name is Mike Stengel. Like Professor Gerard said, I'm a senior in Aerospace Engineering. Today I'm just going to give you the pilot's perspective of how things work. I know there can be a gap between engineers and pilots sometimes, so I'm just here to bridge that gap a little bit. So two things before I get started. We're going to be covering a pretty diverse material. Hopefully it won't, you won't walk out of here with a headache. But just hold all your questions until the end of the class. I have the slide numbers on the top right of the page, so you can just write it down, write your question, and then we'll get back to it at the end. And then just advance warning, forgive my use of the phonetic alphabet. It's just a pilot thing. So when I'm describing airspace letter, I'll say, instead of class A, I'll say like class alpha. So that's just something we learn. It's just a habit. So a little bit about who I am. Again, senior in Aerospace Engineering. I've always had a focus on commercial aviation, general aviation. I guess I evolved. My interests when I was really young went from trains to ships and then airplanes stuck. I currently work at ICF SH&E, which is an aerospace industry consulting firm in Ann Arbor. They were formerly known as Aero Strategy. I believe the founder, Kevin Michaels, is actually coming this Friday to speak at an Aero 285 seminar. So if you're interested at all about learning about a little more on the business side of things and see how the market forces influence the direction of the industry, then I encourage you to go hear what he has to say. And then I also interned with United Airlines last semester from January to May at their San Francisco maintenance repair overhaul facility. They do component maintenance along with airframe maintenance, but I worked in the jet shop, so I worked on auxiliary power units and the main engines for the 747, 757, 767, and 777. Those are all Pratt & Whitney engines. And then most relevant to this lecture, I'm a certified flight instructor, and I'm certified to fly. ASL means airplane single engine land, so anything with just one engine under 12,500 pounds, and I'm also instrument rated. So why I'm here. Like I said in the beginning, as engineers, there can be a gap, so you need to know what your end users are, how they operate. You need to know what rules they operate under, what kind of environment they work in, etc. And then to know those rules, you either need to do a lot of research or you need to have first-hand experience. So again, I'm here to give you a shortcut because obviously not all of you are going to go get your pilot's license. And then I also want to provide you some exposure to current issues and developments, challenges, and then of course make you a better engineer, because a definition of a good engineer is someone who's concerned with applying scientific knowledge, math, and ingenuity to solve or to develop solutions for technical, social, and economic problems. So you're kind of considering all things in the spectrum. So 3 goals for this lecture. First, we're going to overview federal aviation regulations, regulatory authorities. I won't try to go too deep into it because I know it can put a lot of people to sleep. This is the federal aviation regulations. That only applies to the pilot, doesn't even include the airworthiness standards. So this is something I have to review almost every year. But I'll pass that around if you guys want to look at it. And then next we'll go into a typical flight, and I'll provide an insight of how pilots work. And then lastly, I'll go into some examples of engineering applications in aerospace and go over some current developments. So I know I'm actually in the aircraft dynamics class with Professor Gerard, and we actually have it at 1:30 as well. Common problem is that around this time, everyone's just had lunch, everyone's a little sleepy, so I'm going to try to wake up your minds a little bit and just warm up before we get started. So first, I hope you all know this. True or false, a stall is when the engine quits. Thank you. False, it's when the wing or airfoil reaches its critical angle of attack and no longer producing sufficient lift to maintain a certain altitude. And as you can see, I'm sure most of you know this, again, your critical angle of attack is when you reach the peak as a function of your angle of attack, or your coefficient of lift reaches a peak. That's your critical angle of attack. And then you can see over there, as you increase your angle of attack, your air separates and you're actually just producing more drag than lift. But stalls can also be induced by excessive turns. When you enter a turn, you're reducing your vertical component of lift, which is what actually keeps you at your altitude. And then your other component is your horizontal component, which is actually pulling you into the turn. And then the vector sum of those forces simulates an increased weight, and your stall speed is a function of weight. So as your weight increases, so is your stall speed. Like in a Boeing 747 that's going across the Pacific, it'll be at max gross weight like 850,000 pounds. Their stall speed is much higher at that weight than when they land after they burned a lot of fuel. And then I have a short video. There's also uncoordinated stalls, which can be especially dangerous. So this is a video I took when I was getting my flight instructor certificate. It's pointing out the nose of the plane. We have to learn how to recognize spins, which is when you have unequal airflow over both wings. And so one wing stalls more deeply than another, and then the plane just auto-rotates. And then if you're curious, the acronym for the recovery is actually PRAY. It's power to idle, rudder opposite to the spin, neutralize your aileron, so just keep your yoke neutral, and then back pressure on the yoke. So power, rudder, aileron, yoke. So here we go. You'll hear that's a stall horn going off in the background. And I'm entering a spin there. I'm losing about 200 or 300 feet per rotation. You can hear I pulled it at power to idle, and then recovered, and then once I recovered, I'll increase the power again. Lost one more. Again, there's the auto rotation. You see that what's causing that is at the high angle of attack and low power, there's a lot of torque being produced from the engine. And then once the wing stalls, it just pushes the plane over into a left turn. It's one of the left turning tendencies of the propeller engine. So it's a little scary the first time you do it, but not so bad once you've done it a couple times. It's actually pretty fun. All right, so moving on. First thing, going over regulatory authorities and federal aviation regulations. Let me get caught up here. So there's a lot of regulatory authorities in the aerospace industry. You probably know a lot of them, especially the domestic ones. There's the Federal Aviation Administration, which is based in Oklahoma City. And then there's the National Transportation Safety Board. The FAA is more of the rule enforcer and implementer, and the NTSB is the accident investigator. But there's also a larger framework on the global scale. There's ICAO, the International Civil Aviation Organization. That's part of the United Nations. It was founded as a result of the Chicago Conventions in 1944. And then there's the European Aviation Safety Agency, which is similar to the FAA for the European Union. That's based in Brussels. And then there's many other civil aviation authorities for individual countries. So for example, there's the DGAC in France. Don't ask me to pronounce that because my French accent sucks. And then they all have their own defined rules. So ICAO is, ICAO has two goals: the development of civil aviation on a global scale in a safe and orderly manner, and then the cooperation between countries. So they're the ones who implement kind of bilateral agreements. So for example, the FAA and EASA in Europe have bilateral agreements for airworthiness standards to kind of speed up the process especially between Airbus and Boeing aircraft. And then FAA oversees the whole spectrum of aviation activity just in the US. That's their jurisdiction. And then again, there's EASA and the other national civil aviation authorities which establish their own rules that each operator in their country must follow. So while the spectrum is broad for the FAA jurisdiction, we're just going to focus on airworthiness standards right now. So keep this in mind for if you stick with aerospace and you go into 481, that's aircraft design. This might be useful for you because it has a lot of the design requirements to be met by aircraft. And then they're split up into various categories, mainly by weight. So Part 23 covers small aircraft, so like the ones I fly, the little single-engine four-seaters, mainly under 12,500 pounds. Then there's Part 25, which covers the large transport aircraft, like Boeing jets that you would fly on across the country. Then Part 27, 29 cover helicopters, the main difference being whether they're small trainers or large transport category. And then there's Part 33 for aircraft engines. I got another video for you. So this is an example of a Part 25 test. It's called a static test. Many of you might have seen this video. So this is the test for the 777 wing back in, I believe, 1994 and 1995. So they bend the wings all the way up until they fracture. And what they're looking for is satisfaction of the 1.5 safety factor requirement. So it has to withstand 150% of the load. So they already satisfied it, now they're waiting for it to break.
152.
Whichever way you looked at it, the test was a success.
154.
So you'll be hard-pressed to find a situation where your wings are ever going to bend that much in real life. But again, that just shows that's a good example of how safe aviation really is. And then airworthiness doesn't stop during the manufacturing process. It's actually continues throughout the lifetime of an aircraft. So between, have the timeline for right here. So between here and time 0, that's when the manufacturer is talking about designing the aircraft, and then at time 0, they have the design frozen. That's when they begin the design and type certification process right here. That's actually a 5-year process, and if they forecasting delays, they have to reapply to the FAA to meet the 5-year requirement. So at the end of the 5-year requirement, that means they have met all testing requirements and they're issued a type certificate for that one aircraft. And then maybe a year or so later, it'll enter service. That's when a certificate of airworthiness is issued. That's issued to each operator. And then from here on, it's until the end of the life of the aircraft. The aircraft is under the operators, so like the airline's jurisdiction. So they have to make sure they have a maintenance program that they can impose and meet all of the safety requirements. So continued airworthiness can include satisfaction of airworthiness directives. So that means the FAA can send out a notice to operators of a certain aircraft that says, hey, we know about a certain problem. You have this amount of time to fix it, or else the aircraft is no longer airworthy. And there's other examples too, like supplemental type certificates, which is when the aircraft undergoes a major modification. And everything you see inside an airliner, everything from the seats to the interiors, has to be certified and tested. And that's part of the reason why it's so expensive too. So a good example of that in real world is, you might have heard about this recent American Airlines trouble with the seat racks. That's an example of faulty continued airworthiness. So here's an example of a type certificate. Like I said, this is issued to just one type of aircraft. So a Boeing 777 has one, a 747 has one, all Airbus type aircraft have one, and they're issued by what's called a state of design. So that would be the FAA or EASA. Each agency has to issue a type certificate for the aircraft to be allowed to fly in its jurisdiction or airspace. So this is an example of Dornier 328. That's a small turboprop regional aircraft issued by the FAA and DOT. And then next is the airworthiness certificate. So again, this is a certificate issued to each individual aircraft. So it's actually in the regulations that all aircraft have to have this on board. So here you can see the registration, make and model, and then any special requirements it has to meet, and then date of issuance and whoever certified it. And those are issued by the state of registries, so that includes FAA, the DGAC of France, and all those agencies. So moving on, the regulations also cover Part 61, which is certification. That's for pilots, flight instructors, and ground instructors. Also defines the flight experience that you have to meet in order to apply to take the test to acquire those different licenses or ratings. And then in addition to that, you have to be healthy enough to be able to acquire a certificate. So you actually have to go to a special FAA doctor who will examine you, just a quick checkup, make sure that you're healthy, they won't pass out during the flight and all that. So here's some basic requirements that you have to meet to acquire these different licenses. So when you first start out as a student pilot, and that's the student pilot certificate is basically your license to solo. It's not actually an FAA license. It's issued by an instructor at his discretion when he believes that you're ready. It's typically issued around 10 or 15 hours total time. So you've done a couple landings, you know how to fly the plane, you know how to talk to air traffic control, just the very basic. You're not allowed to go in any busy airspace, and there's very restricted privileges. And then third class certificate. So the medical certificates, they all have the same standard, but the different classes differ on how long they're valid for. So third class certificate is good for 60 calendar months, so the last day of the 5-year period, last day of the month of the 5-year period. And then your private pilot certificate requires 40 hours total time, also third class medical certificate. And then your instrument rating, which means you can fly in poor weather, you need 40 hours additional time of instrument training with an instructor. And then your commercial license allows you to fly for hire, which means you can get paid. And then that requires 250 hours total time. And second class medical certificate. And then finally, flight instructor just requires your commercial license. And then these where the big boys are flying the Boeing jets, 1,500 hours total time and first class medical certificate. So these guys have to, if they're over age 40, they need to renew their medical certificate every 6 months. And then I have a flight instructor certificate, and I have about 340 hours. Where are we? And then I'll just give an example of some of the requirements I need to meet in order to stay legal or proficient. So that's another thing the FAA emphasizes is flight proficiency and recency of experience. The saying goes that flying is like riding a bike, you never forget, but if you haven't been flying for 6 months, then you might be a little sloppy with your maneuvers and your landings and some of your air traffic control phraseology. So I need to, in order to keep my flight instructor or commercial license valid, I need to do 3 takeoff and landings every 90 days. And then if I want to fly at night, I also need to do 3 takeoff and landings at night as well. And then for my instrument rating, every 6 months I need to fly 6 instrument approaches and then practice holding procedures and intercepting and tracking courses. And then I also have to renew my my flight instructor certificate every 2 years with by doing either an FAA refresher course or if I meet a certain passing rate of students, like I think it's if 4 out of my 5 students within the last 2 years have gotten a license, then I'm covered then too. And then I also need to complete a biannual flight review, so every 2 years with another flight instructor, and then renew my medical certificate every year. So it's a lot to keep track of, and gets kind of expensive after a while. So next we're going to outline aerospace structure. Some common misconceptions about aerospace is that it's uniform, that they all provide, it's the same service across the country, which is not the case at all. It's actually broken down into different segments based on the region and the volume of aircraft that flows through a certain area. Like I said. And then there's actually also a lot of uncontrolled airspace too, especially out towards the Rocky Mountains, where the terrain is very rough and there aren't many big commercial airports. So here's a visual breakdown of different classes of airspace. So I'll go through in alphabetical order. So Class A or Alpha airspace is where you see a lot of airliners. The minimum altitude is 18,000 feet and goes up to 60,000 feet. What's required in here is an IFR flight plan, which means you submit a flight plan to the FAA and you're always in constant contact with air traffic control. Next is your Class Bravo, and that's mainly the airspace around busy metropolitan areas. So there's a Class Bravo for Detroit, New York, Los Angeles, Chicago, all those busy hubs. And the floor is from the surface down, and then up to 10,000 feet is a ceiling. And then that's a 20-mile radius, and then again, you always have, if you're inside this, what we call an upside-down wedding cake, you need to always be talking to air traffic control as well. And then Class Charlie and Delta, that's what we call wannabe airspace. So a Class Charlie is a wannabe Class Bravo because it's a smaller airport, but maybe not as big of a city. But it has the same services as Class Bravo, but a little less restrictive. And then Class Delta, Ann Arbor's a Class Delta airspace. That's controlled as well, and 4-mile radius, and typically goes up to 2,500 feet above the ground. And then every other airspace is Class Echo. That's very broad. It covers a lot of the United States. And then, like I said, there's the uncontrolled airspace, Class Gulf, which is out towards the Rockies. So you might notice the ceiling for this is pretty high. It's 14,500 feet above sea level. But keep in mind, too, that out towards the Rockies, the base altitude can be pretty high above sea level, too, like maybe 7,000 or 8,000 feet. So it's uncontrolled. They don't have to talk to air traffic control, or the pilots operating there don't have to. And then I don't want you to freak out over this. This looks really busy, but the idea I want you to walk away from this slide is that there's a lot of requirements to be met when you want to fly in certain airspace. Everything from ATC requirements, whether you need to talk to a controller or not, to certificates. So like I said, a student pilot can't fly everywhere. They have to receive special training if they want to fly in that really, really busy airspace around big cities. Radio communication requirements. There's visibility requirements, and you have to maintain a certain distance from clouds. And then all that. And here's some services the controllers provide in different airspace. Then there's also special use airspace. So one example is the Air Defense Identification Zone. So that actually extends across all coasts of the United States. And an example I'll use in a second is the Washington, D.C. airspace, which is very security restrictive. There's also restricted areas that can include airspace around power plants, national laboratories, and so on. Prohibited areas, as the name implies, you cannot fly there under any circumstance. That includes airspace around Washington, D.C. Mall, so White House, Capitol, Washington Monument, all that. Then there's special flight rules area. So this is airspace where it might be tight and requires some extra training. So one example of that is, so you all remember where you heard about the U.S. Airways A320 that landed in Hudson a couple years ago? This is an example. He landed in that special flight rules area. That's actually a really high density route or corridor for small aircraft to fly through the New York airspace. You can fly right along the Hudson River, right next to the city, and it's like 1,200 feet above the water. It's really cool when you fly along it at night with all the lights and everything. I've done it a couple times, but it requires special training because of the high density, the density of aircraft in that area. And you're not talking to an air traffic controller either, so you need to know the landmarks that you need to fly along to maintain separation. Then there's military operations areas where U.S. Air Force will conduct practices. There's some in Indiana. There's basically the whole state of Nevada is one big MOA. And then there's temporary flight restrictions. So let's say the president is visiting, they might impose a flight restriction saying no aircraft can approach a certain radius of a certain airport in a certain time frame. There was one time I was flying, so I'm from Pennsylvania, and when I was building my time, I would fly to Jersey Shore a lot, just fly down, fly back. And then that route takes me by Philadelphia a lot. And there was one day where Air Force One was visiting, and the controller wouldn't let me anywhere close to the airspace. They actually had to make me go all the way around the airspace and added like a half hour to my flight time. So this is the Washington, D.C. Air Defense Identification Zone. So this outer radius is a 60-mile radius around Reagan National Airport. That's right next to the Washington Mall. So I can fly in this outer core as long as I maintain constant communication with air traffic control, and I submit a flight plan, and they issue me a discrete transponder code. So that's unique to my aircraft, and as long as I'm talking to them, I won't have F-16s flying by my side. And then this inner core is a 30-mile radius around Reagan National Airport. This is called the flight restricted zone. You cannot enter this airspace unless you go through a 6-month background check and you get a special individual PIN number that they give to you, and you have to put on your flight plan so they know exactly who is flying into that airspace. I heard a story about a US senator who tried flying into this FRZ, and he didn't go through the background check, and they wouldn't even let him in. And I hear about small aircraft once in a while who don't know the rules, and they'll penetrate this airspace either without a flight plan or not talking to a controller, and you'll see Blackhawks next to a little 4-seat Cessna 172. So it can be a little nerve-wracking. I flew into a small airport. I think it's right up here. It's called Suburban Airport. When I was applying to colleges, I visited University of Maryland, and the day before, I was planning to fly down, and then I realized I can't fly into College Park Airport, which is just inside the FRZ. And so I had to re-strategize, and I flew into this really small airport, really barren, just outside of that. My parents were a little freaking out a little. They're like, I don't want to see any Air Force helicopters or planes next to us. All right, moving on. Now I'm going to provide an insight into a typical flight, what I go through when I plan a flight, execute it, and the kind of things I'm looking for. First, some misconceptions about pilots. There's the idea that pilots or autopilots do everything, so what's the point of a pilot anymore? I will say many of the planes I fly don't have autopilots, but they are common in the larger airliners, but they're also needed in larger airliners because those are also very complex, very fast, and autopilots help reduce the workload. But even if we're not flying the plane manually, there's a lot of tasks to be completed. You need to be talking to air traffic control, keeping track of the weather, keeping track of where you are, always have in mind a place to divert if you need to go somewhere if there's an emergency. And then we just proved that radar air traffic control isn't always available, especially for small aircraft. For the larger jets, that may be the case, but then in summary, I think this pretty much sums it up. The public thinks we're just lazy and we're falling asleep at the controls all the time. So to characterize it in an accurate way, pilots have a large emphasis on safety and knowing our limits. And then there's recency of experience we have to keep in mind. Do we feel comfortable completing this flight? Do we feel capable of doing it? There's also quick decision making. There's an emergency in the air. You need to assess your options, make a decision. There are some times where it has to be faster than that. There's one time especially, I was actually flying back from here, back to Pennsylvania, along Lake Erie near Sandusky, Ohio, and all of a sudden the air traffic controller tells me there's an aircraft like a mile ahead of me, same altitude, opposite direction. So that wakes me up a little, and 2 seconds later, see a guy coming straight at me at 5,500 feet, and that's when your training kicks in, and luckily we both remember to pull a right turn. That's what you're trained to do. So that's a right-of-way maneuver we're supposed to remember. Like I said, proficiency of recent experience is important, along with situational awareness. So can anyone define for me what they think situational awareness is? Any idea? So basically, it's you're assessing the environment around you and then coming up with a get-out plan, and then forecasting the future state of your aircraft. And I'll go over that a little bit later. Then, of course, you need to stay up to date with current regulations. Ask questions like, am I legal to fly? And am I allowed to do this? There's also Part 91, which pilots have to keep in mind. That's part of the regulations again. So just the basic operating rules. I won't go too into it because it's really broad, but one quick example is fuel requirements. So Part 91.151 says we cannot fly VFR on any, conduct a flight at all unless we have enough fuel to fly to our airport and then thereafter for at least 30 minutes during the day or at night for at least 45 minutes at cruise speed. And these planes, burn about 10 gallons an hour, or the ones I fly, so you need to account for that. Then there's IFR versus VFR. So IFR stands for Instrument Flight Rules. So this is when I have no reference to the ground. I'm just looking at the clouds, or I'm above the clouds. And the legal definition of it is visibility less than 3 miles or cloud ceiling less than 1,000 feet. Then the opposite end of the spectrum is VFR, Visual Flight Rules. That means I always have a reference to the ground. I can fly or via landmarks on the ground, follow an interstate or something. And as you can see here, it's clear weather, visibility greater than 3 miles, cloud ceiling greater than 1,000 feet. So with all those things in mind, I go into a pre-flight. One example is a flight from Ann Arbor to Chicago, let's say Midway Airport. The aircraft is a Piper Aero that I fly. That's the registration. First thing I look at, even before I'll start looking at the weather days before the flight, just to keep an eye on it. So this may look confusing to you, but this is a typical format for the weather report. So this is staying at this is the Ann Arbor station at, here's the date, 15th October, the time in UTC time. This is the wind, so we're showing a wind out of the northwest at 15 knots, gusting to 19 knots. Visibility is 10 miles or greater. Overcast clouds are reported at 2,400 feet. Temperature is 10 degrees Celsius. The dew point is 4 degrees Celsius, and the barometric pressure is 29.85 inches of mercury. And the same format follows for Midway Airport in Chicago, and then this is the forecast. So based on this, my clouds they're not too low, but it's what we call marginal VFR, so it's below 3,000 feet. So this is when I would consider following an IFR flight plan, because I may not be able to stay clear of the clouds the whole time. Then I plan a route. So here's Ann Arbor, and then here's Chicago. It's not actually a direct route. There's actually a big network of airways across the United States. So looking at my chart, I see that I can fly to, this is called a Litchfield VOR. A VOR is basically a ground beacon that emits a signal used for navigation purposes. We can fly point to point or along a certain airway. So I fly direct to this VOR, follow the Victor 10 airway to Goshen VOR, that's right by South Bend, Indiana, and then a straight shot across Lake Michigan, still following Victor 10 to this intersection called Niles, and then to Midway Airport. Then another part of my pre-flight tasks is to do weight and balance calculations. So obviously you can't stick as much or as many passengers as you can into an aircraft. There's weight limits to keep in mind. So the weight limit for this Piper Aero is 2,750 pounds. And then I have to also calculate the center of gravity because that influences the stability characteristics of the aircraft. So here I see at takeoff, I'm right at just below the maximum gross weight, and I'm within the envelope. My center of gravity or aircraft arm is within the appropriate limits. Then as I burn fuel, my weight decreases and my center of gravity is still within the envelope. So this is the format for a flight plan that I submit to air traffic control. This is just a paper version. There's online resources too. I can do it much faster now. So I click IFR flight, I put in the aircraft registration here, type of aircraft, the expected airspeed I want to be cruising at, departure airport, expected departure time, my cruising altitude. For that direction, if I'm flying westbound, I want to fly at even altitudes. So I'd probably pick 6,000 or 8,000 feet depending on the conditions and how my aircraft will perform. The route of flight, I would enter in what I just showed you on the previous slide, followed by the destination, Midway Airport, estimated time and route, just under about an hour and a half. Any special remarks? Probably none for this flight. Then fuel on board, about an hour and a half. I wouldn't go on this flight with anything less than 2.5 hours worth of fuel. Then I also have to submit an alternate airport, so I could say there's Gary Airport in Indiana or O'Hare Airport right next to Midway. And then my name and destination contact, all that. Then other things to consider during my pre-flight, there's notices to airmen called NOTAMs. This is issued by the FAA on a daily basis. This includes information on out-of-service VORs or if there's certain airspace I should avoid. There's pilot reports, which pilots individually submit during a flight, and then the FAA publishes them. So this can include reports on any turbulence, icing, any areas that I might want to be concerned about and maybe avoid too. Temporary flight restrictions, like I mentioned before, any restricted airspace, maybe the president's visiting, maybe there's an accident and they have the airspace blocked off. Restricted airspace, if that's active or not. And if all that's good, then I head out to the airplane. So the first thing I do when I get to the airplane is called a walk around. You might see pilots that, with big airliners do this too. There's kind of needlessly kind of walking around, but they're actually doing just a standard check. It's not meant to be too thorough. You check fuel and oil systems, any obvious leaks, you check the avionics, and any significant damage. It'll be hard to spot something, that's internally engine or internal to the aircraft. Many of the things you can't figure out until you either start the engine or maybe you're in the air. Then start up, go through my checklist, start my engine, get my route clearance from air traffic control, and then contact Ann Arbor ground frequency to get my clearance for taxi. Taxi to the runway, call the tower, get my takeoff clearance, and then right after takeoff, the tower will hand me off to my departure frequency, which here would be Detroit approach. And then they'll clear me onto my followed route and up to my cleared altitude. Then en route, like I said, climb to my cleared altitude, about 6,000 or 8,000 feet. I'll set my power setting based on, maybe I don't want to burn so much fuel, so I'll fly a little bit slower, but it'll take longer to get to Chicago. It's not like I showed you before, it's not a straight shot to Chicago, so I have to navigate point to point to those different VORs, so I need to always keep track of where I am. About every 30 minutes I need to switch my fuel tanks, especially since it's a low wing aircraft. It's not gravity fed like a high wing Cessna is. And then I'm always looking out for other traffic. This is important because there's the misconception too that as long as you're talking air traffic control, they'll keep you safe from other aircraft. The example I gave with you about the near mid-air collision I had over Ohio, that disproves that theory, because as long as I'm outside the clouds, I'm legally responsible to watch out for other aircraft and visually avoid them. But if air traffic control is able to, they'll also give me notice. And then I have to get updates in weather as well, especially if it's looking marginal at my destination. This is important too during the summer when thunderstorms can pop up at almost any given moment. So I'm going to pass around my iPad. I have my digital charts on here, and you can play around with a sectional chart just to get an idea of what pilots look for and what we work with. Let's see. So the map is going to be centered on Ann Arbor Airport, and you'll see the Class Bravo airspace around Detroit. So you can pan around it with your fingers and everything, and zoom in and zoom out. So I went over a little bit before. These beacons called VORs, that stands for a VHF omnidirectional range. It's a ground beacon that emits a degree in 360 degrees that aircraft can use to track to or from that station. So there's Litchfield VOR, and then Victor 10 Airway connecting Litchfield and Goshen VOR, and then Victor 10 Airway again connecting Goshen to this last waypoint on my flight plan, Niles. So with my course deviation indicator, I can center in on a special course. So I can say, I want to fly, so if this is north, east, south, and west, and 090 is your east heading, this would be about your 080 radial from that station. So imagining a line pointing from the center of this circle right here. That's your 080 radial. I can say, I can tune in to the 080 radial and then center my CDI and then just fly that course. And then if I go left or right of that course, it'll tell me immediately, and then I just turn the aircraft as I need to recenter myself on that course. After I pass over it, I can readjust the course deviation indicator to say I want to fly now that would be about the 250 radial from Litchfield to Goshen, and then do the same thing again when I cross Goshen VOR to Niles. And then the way I find out if I'm at this point or not, since it's not a VOR, I can use either my distance measuring equipment or DME. I know the distance from here to here, so as long as I'm centered on this course and I know the distance, I can determine when I've reached that waypoint. Or I can use a crossing radial from another VOR, such as this one. This is Chicago Heights. And then if I weren't going VFR, I don't have to follow this planned route. I can plan my own route using landmarks and all that. If I wanted to, I could follow I-94 all the way from Ann Arbor around Lake Michigan to Chicago. It'd be that easy. Then as I'm approaching Chicago, I'll get in touch with Chicago Approach. They'll give me instructions where to go, which headings to fly, which altitudes to descend down to. They'll line me up with the runway basically, or I can fly either a visual approach or I can fly this approach. It's called the instrument approach. This is something I can fly using my instrument rating. So basically there's a radio that emits a signal. This is called a localizer. That lines you up with the center line of the runway. And then this is called the glide slope, which gives you the proper glide path down to the runway. And it's very accurate, very sensitive too, but you can fly in the clouds without any reference to the ground. You pop out of the clouds at 200 feet, and the runway will be centered right in front of you, and you'll be on the proper glide path. And then, in addition, one of my tasks includes setting up for the approach, always staying ahead of the airplane. I always want to know where I'm going and where I'm going to end up. And then flying the approach, I have to maintain my airspeeds to fly a stable approach, so I'm not coming in too fast or too slow. And then if something goes wrong during the approach, I can abort it at any time, and it's called a go-around. This is a missed approach procedure for that. Let's see, it tells me to climb to 1,100 feet, then a left climbing turn to 2,100 feet to heading 150, tune in to this VOR radial, so I'm flying the northbound or southbound radial to this intersection, and then climb to 2,600 feet. And then air traffic control will tell me what to do from there. I went through landing already. I call tower, they'll clear me to land. I'll set my airspeed, stable rate of descent and all that, and then go around if I have to. So just to keep in mind, this example is with a very basic aircraft with little redundancy. A Piper Warrior like this has just a battery and alternator for an electrical system. You don't have a backup. If I lose my alternator, I just have to know that I have 30 minutes of battery life left, and then I have to land during that time. in larger aircraft with more redundancy, there's more knowledge requirements, and you need to be able to prioritize and work with your co-pilot to complete a task. It's never a one-man show, at least in those larger airliners. And then this is something I asked you about earlier. It all comes down to situational awareness, which has 3 parts to it: the perception of elements around you, the comprehension of their meaning, and then the projection of their status in their future. And I know that engineers like feedback loops, so I included this. You have a goal, so you assess everything around you, perceive, understand, think ahead how it's going to be, implement it, and then see how the result is. If it's not working, then you try it again. It's an iterative process. All right, next thing. All right, doing well on time. I'm going to give some practical engineering applications in aerospace and give you a clue on some current developments and challenges. So there are many fields you guys can study as aerospace engineers. There's aerodynamics, structures, propulsion, basically anything. But right now we'll focus on aerodynamics. So can any of you, just by looking at an airplane, is there anything you can tell me that is a design feature that affects the aerodynamics of an aircraft? What was it? Winglet? That's one of them. Good. Can you tell me more about that? Good. Yep, that's exactly it. I'll cover that in just a second. So, like I said, I'll go through some examples. Think about how these might be important to a pilot. So, first thing is there's angle of incidence and wing twist, or it's called washout too. So you can see here at the root of the wing where it attaches to the fuselage, the angle of attack is greater than the tip. Does anyone have any idea why that might be important? Okay, so everyone knows that lift is a function of angle of attack, right? So if I'm maintaining an altitude but a high angle of attack and I'm about to stall, what happens is the stall happens here first because the root has a higher angle of attack than the tip. So the root will stall first and then move out towards the tip as the wing stalls more. Why would that be important? Anyone have any ideas? Yep. Exactly. That's exactly it. So you can see here, along towards the end of the wing, you have the ailerons. Ailerons control your roll movement, and it's paramount during a stall that you have that roll control. Otherwise, you can enter what I showed you before, that spin. And so by having the angle of attack lower at the tip than at the root, I maintain aileron effectiveness throughout the stall. All right. Oh, another thing too is that the higher angle of attack here will buffer. It'll provide a buffer to the fuselage. So as I approach a stall, the air becomes turbulent over the top of the wing, and that makes the airframe shake a little. And then that gives me a clue that a stall is imminent. It helps me prepare, even if it's just a few seconds. Next thing is dihedral and anhedral. So if you look at a plane, you might notice that the wings are angled up from the horizontal plane a little bit. Any idea why that might be important? What's that? Not exactly, but it has to do with lift. Yep. The stability, exactly. So let's say I'm looking down at my instruments just for a few seconds, and I inadvertently turn the yoke this way and I go into a roll, or the aircraft might naturally go into a roll if I take my hands off the controls. As long as the roll is within 15 or 30 degrees, the bottom wing, or the inside wing in the turn has a higher angle of attack than the outside wing, so that produces more lift on this wing than this wing, and so that induces a rolling moment which stabilizes my aircraft to a level position. And then the opposite is anhedral, which is the wings are angled down compared to the horizontal frame or horizontal plane. That would be important because this is a fighter aircraft, it's a Harrier, you want that kind of maneuverability, because in this case, the natural tendency of the aircraft is to stay level. If you had that in this aircraft, you'd be fighting it the whole time, where you want to be able to pull those, those barrel rolls and all that. So you mentioned before winglets. What winglets do is reduce induced drag, which is drag as a result of producing lift. One way of solving that problem is to add these winglets, which, well, the way to, ideally, to get rid of these vortices, this induced lift or induced drag, is to make the wingspan infinite, which obviously is impossible because it's materially impossible, but there's also gate restrictions at airports and all that airlines have to meet. But these winglets have been one way of increasing the span and reducing this drag. But why would that be important to a pilot too? So one thing this type of drag, these vortices also produce, is a type of turbulence called wake turbulence. And it's especially prominent when the aircraft is heavy and it's taking off at low speed. And so there'll be a picture on my last slide, but you can see them when they're approaching the airport, and they actually emanate behind the aircraft too. You're taught as a pilot that you need to avoid these vortices, especially with these large aircraft. Like if a Cessna 172 is taking off behind a 747 that's going around the world, that can be really dangerous because I can get caught in those vortices, and it can be like, it can roll me over, it can push my altitude down. One example of that is, I don't know if you guys remember this, but right after September 11th, there was a crash, American Airlines 587 and Airbus A300 crashed right after takeoff from JFK Airport in New York. What happened was, same situation, a Japan Airlines 747 that was heavy and slow was going to Tokyo, took off, it produced that wake turbulence, and that Airbus took off right after it. He got caught in that wake turbulence. Now, the wake turbulence wasn't the reason he crashed. It was actually because the pilot used too much rudder and oscillated too much, which put too much force on the rudder, I guess, and ripped it off. And that's the reason it crashed. But wake turbulence was a factor. So again, this would be important to a pilot because less drag means increased performance, but also less wake turbulence, and it's safer for us. There's also the field of structures and materials. You all probably know about the Boeing 787, how it's revolutionary because it uses a lot of composite materials, which make it lighter, more fuel efficient, and so on. So here's a breakdown of the materials used in the aircraft, and then take a note here. By comparison, the 777 has 12% composites, 50% aluminum. That's a huge undertaking with materials and makes these aircraft more efficient. There's also a lot of activity recently in the field of propulsion. If you didn't already know, engines typically make up a third of the cost of an aircraft, and it's more important these days because fuel's more expensive and airlines are demanding that these engines be more efficient than ever. So over time, the technology has evolved. And one way that has evolved is with bypass ratio. So maybe despite common intuition, not all of the air that passes through an engine passes through the core here. By the core, I mean the compressor, the combustor, and the turbine. There's actually a fair amount of air that passes around it. That's called the bypass ratio, the mass flow rate of the air through this bypass over the mass flow rate of air through this core. These days, engines have a BPR of about 9 or 10, but here you can see back in 1963 when the Pratt & Whitney JT8D came out, which was a common engine on Boeing 737s, 727s, and I think there's a DC-8 in this aircraft. The BPR was 0.96 to 1. So that has increased over time to the GE90, which is the primary engine for the 777, to a bypass ratio of 9 to 1. So some advantages to increase bypass ratio is that you have a leaner fuel mixture, which increases your fuel efficiency, increases thrust, and you also have decreased noise from the engine because that air flowing around the core of the engine acts as, acts as like a cushion to the air, the hot exhaust air that's coming out of the turbine. And then just another visual. And you can see here, this is the Pratt & Whitney geared turbofan. You can see here, right here, this is the core. And then out here is the bypass. So just gives you an idea of how much air really goes around it compared to through the middle core. Then, like I mentioned, there's the geared turbofan. So there's been two kind of philosophies of how to increase engine efficiency. One of them has to use better materials in the turbine to increase that temperature there. If you didn't already know, the temperature in the turbine is actually hotter than the current materials used there. It's hotter than the melting temperature of those materials. So the way they solve that problem is the blades are cooled by having a thin film of air go over them. But they would like to increase that temperature. It makes it more efficient, produces more thrust, but that's really hard to do with ceramics. So the other philosophy is to optimize the speed of all the shafts in these different sections. And the way Pratt & Whitney is doing this is with the geared turbofan. So they're using this gearbox at the inlet to optimize the speed of all the shafts. That reduces, in turn, the number of stages, which reduces the manufacturing costs. And it also reduces the speed of the inlet fan. And the idea is to take a big, slow fan and shove air into a small, fast turbine. And then it's just, all it is simple gear reduction principles. And then other advantages include there's reduced noise, and then since this fan is moving slower, that means the life is going to be longer. That's reduced maintenance costs too for the operators. Another development is with fuel. May not have heard about this because general aviation tends to not make the news a lot, but Cessna recently came out with a modified version of their 182. Their traditional versions used fuel called 100LL, that's low lead. It contains a toxin called tetraethyl lead. It's used to enhance combustion stability, but it turns out that Jet A fuel, which is basically pure kerosene and used by jet engines, diesel engines, is actually cheaper than 100LL avgas, it's called. And it increases performance. So the NXT uses Jet A, and then the traditional 182 Skyline uses 100LL. So Jet A is cheaper, it's more widely available, and increases your performance pretty significantly. 145 to 155 knots may not seem like a big deal to you, but to me that's really exciting. I love to go faster in these small planes, and of course you're burning less fuel, you can go to higher altitude, and you can go farther. Next, with avionics, if you look how avionics have developed over the last 40 years, it's been pretty amazing. It's increased safety, reduced the crew workload, increase or decrease operating costs, and increase the amount of information available. Again, emphasizing situational awareness. The more information that's available to pilots, the better. 40 years ago, pilots didn't have weather radar. They would have to, spot the thunderstorms visually and then just fly around them. There's been traffic collision and avoidance systems. I think I have them here. Yep. So some developments have been weather radar, traffic collision avoidance systems, flight management systems, LCD displays, and digital charts. All those have made the pilot's job easier, increased the safety level too, and reduced operating costs. So just to quickly visualize it, this is the Boeing 747-100, which was first manufactured in 1969. If you look at this flight deck, it looks pretty basic, right? A lot of analog instruments. This panel right here is where the flight engineer sat. That's the third pilot. There were, I think, over 1,000 switches and dials to be dealt with in this version of the 747. It's since been improved, but this is what they had to work with back in the day. Then came along the Boeing 757 and 767, which was revolutionary in the sense that they implemented systems called the EFIS, the Electronic Flight Instrument System, I think it was. Let me double check that. Yep, Electronic Flight Instrument System, and the ICAS, the Engine Indicating and Crew Alerting System. So basically it got rid of the flight engineer's job, reduced the number of required pilots down to 2, and put all the information that the flight engineer would normally provide into these 2 displays. Manageable for pilots, for 2 pilots to handle. And of course, for airline management, less pilots required, the better, because that means less cost for them. And I think they reduced the number of switches and dials by like 600 just by using this setup rather than the previous one I just showed you. Then last, there's the Boeing 787. This should be a stark contrast to the previous aircraft. Big LCD displays, very digital. You got your electronic flight bag, which you can store all your charts in. There's SATCOM, which you can call your company dispatch to report a problem. There's text messaging you can use with air traffic controllers in areas like when you're flying over the Atlantic where there's no radar, they have to do position reports. Normally they would use an HF radio, which is very staticky. It's really hard to communicate with. Now that you can use a text message system. So that's some of the features of more advanced avionics. And then another field of study in aerospace engineering is human factors. You might see a lot of, mainly IOEs are typically associated with this, but there's nothing stopping you guys from going to human factors either. So one example of this is there's a professor in IOE, Nadine Sarter, who's doing an FAA study of pilot interaction with next generation displays, and just seeing how pilots interact. And I helped them set up their simulator and ran a couple tests with them. And all they had me do was fly a typical flight and like 45 minutes, and they had me spot if I could see warnings that came up on the display and how fast it would take me to respond to those warnings. And then, if you didn't know, human factors is a study between interaction between pilots and their flight deck environment. Why is it important? Like I said in the beginning, there's a gap between engineers and pilots. Not all of you may think like a pilot, so you need to think like your end user. Put yourself in their shoes. One thing that you think may be good for a pilot may be detrimental to them. And then I'll go into that in just a second. Yep, like I just said. One example of this. This was pretty controversial. It's still ongoing, even though the final report came out. You might have heard about this crash a couple years ago, Air France 447. It was an Airbus A340 flying from Rio de Janeiro to Paris, an overnight flight across the Atlantic. So I'll try to briefly summarize it. The aircraft flew into a region known as the Intertropical Convergence Zone, which is a region of volatile thunderstorm activity because that tends to be where the air is least stable because of the temperatures. It's normally not a problem with weather radar, but somehow they got themselves caught in or near a thunderstorm, and they experienced icing. There are de-icing systems, but there's a probe called a pitot probe, which is used to measure the total air pressure of the air at your altitude, and that is used to measure your airspeed. If that pitot probe freezes, then your airspeed readings are unreliable, and in this case, that's what happened. It froze, and since the computer, the autopilot, couldn't tell which airspeed reading was reliable, it just disconnected. It didn't know which one to believe. And then afterwards, the pilot, maybe because it was as a result of the startle effect, but he entered a climb. I don't know why he would have done that, but that's what happened. And then the climb resulted in a stall, and because of how fast this all happened, and because of other situational awareness factors, he didn't realize that he was in a stall and crashed into the ocean. He was literally pulling back. The pilot flying was pulling back on the stick the entire time, all the way from 35,000 feet down to the ocean. And the proper recovery procedure for a stall is to push forward to recover your airspeed, and then recover your altitude. So why did this happen? Well, the pilot flying had to stick back the whole time. Why didn't the other pilots notice this? Well, in the Airbus, because of the fly-by-wire design and just the overall design of the flight deck, these side sticks which are actually on the side of the pilot rather than in front of him, like you might see in a Boeing airliners. That's the yoke, and then the Airbus has a side stick. The pilot, it's hidden behind his knee, and the side sticks, even though they're on both sides, for the left seat pilot and the right seat pilot, they don't move. Like if the right seat pilot moves it back, the one on the left stays in position. It doesn't move like a yoke would. They're not mechanically connected. So there's that, visual loss. The other pilot couldn't tell that he was pulling back the whole time and didn't realize it until it was too late. And then there are other factors to consider, like they're flying at night over the ocean, no reference to their horizon, and they couldn't tell that they had a high angle of attack and falling. There was a startle effect, which, the pilot, even with all of his training, he might have been scared and just panicked. But unfortunately, even though we recovered the black box, we'll never really know what was going through the pilot's mind at the time. But bottom line is that there are human factors to consider. Like one other quick example is there's a trim wheel, which is used to reduce the forces that a pilot needs to maintain a certain attitude or altitude. In a Boeing jet, you see and hear that trim wheel turn. So you can see it turn like right next to your knee, and there's also like a mechanical sound. So you can, even if you're not looking at it, you know it's moving if you're looking straight out the window. So if you can hear it turning, the aircraft is reconfiguring itself, and you can, that's a situational awareness factor where you can determine what kind of configuration I'm in. In the Airbus, that doesn't move, it doesn't make a sound, so maybe they didn't know like what kind of configuration they were in, and the throttles don't move because of the digital engine controls, whereas in a Boeing airliner, they move even when it's under auto throttle control. So I'm not trying to start an Airbus versus Boeing argument, but those are just some of the differences between the two aircraft. So this is a conclusion. I hope you guys learned a lot. We covered a lot. There's a lot more to learn about if you guys are interested. But what I hope you walk away with is a better understanding of regulations and regulatory authorities, some insight into how pilots work and the type of rules and environment we have to operate under, and then finally an idea of the many fields you guys can go into as aerospace engineers. The limits are endless. That's it. Thank you very much.